Hi, my name is Diana, and today I'll be discussing radioactive decay. So some elements are so heavy and their binding energy is so insufficient that their nuclei actually decompose into different particles over time. So we're going to go over the rules to kind of balance these equations for when this decay does occur. So first, as a refresher, if we were to write out an element, let's just call the element X, and we said A would be the mass number, and Z would be the atomic number. Now Z, as you can see, is a number of protons, and this is really how you identify an element, by the number of protons. Meanwhile, A, the mass number, is just, it's the sum of the protons and the neutrons, but do not make the mistake of identifying an element by the mass number. Again, just number of protons. This is because different forms of elements have different number of neutrons that vary slightly, but the number of protons always stays the same, so that's why we identify elements by their atomic number. So with this notation in mind, we will proceed to balancing radioactive decay equations. So another rule to keep in mind is that the sum of the superscripts have to equal the sum of the superscripts, and this is part of the conservation of mass and energy. Similarly, the sum of the subscripts have to equal the sum of the subscripts. Again, this is part of conservation of charge, because number of protons, again, subscript Z, number of protons has to stay the same. So there are different particles, not just anything can come out of radioactive decay. There are various types of particles that can result. And so first type is called an alpha particle. It has a mass of 4 and a charge of 2. And and then also the beta particle, mass of 0. It's so tiny, like an electron, it's almost negligible mass, and a charge of -1. And then finally, gamma has a mass of 1 and no charge. So actually gamma ray decay is not, it's not mass at all. I'm sorry, it is only mass. It does not change the charge at all. Okay, so with these types in mind, we can start doing problems and identify which particles are being formed as a result. So back over here, let's say we were to have radon, mass number 226, atomic number of 88, and it's decaying into some element, and we know it's decaying into an alpha particle. So because a helium nucleus has a mass of 4 and a charge of 2, we associate alpha particles like a helium nucleus. So if we did this, it's really very simple algebra to figure out which the element is. So first what we would do is, so sum of superscripts has to equal the sum of the superscripts. So 226 equals X, because we don't know what this is, plus 4. And then with simple arithmetic, we know that whatever this is has a mass number of 222. Similarly, 88 equals X plus 2. And whatever this is would have an atomic number of 86. So using the atomic number, we can identify this magical element as Rn. And there you have it. Similarly, if you do another example where the reverse, if we don't know which particle is being decayed or produced, really the same thing, just knowing that the subscripts have to equal each other and the superscripts have to equal each other. For instance, if we have lead decaying a beta particle, just kidding. Let's say we did not know it was a beta particle, but we did know that it would turn into Pa. So since there's no change in mass, but there is a change in charge, this would be a beta particle, as we see over here. Because there's no mass, no change over here, but change over here, there's a change in charge, and that's why this is a beta particle. And that's it.